All right, so part of what contributes to the wide diversity of organometallic complexes are hydrocarbon ligands, right, and derivatives thereof. And so the simplest are just hydrocarbon ligands that undergo bonding in an 8-of-1 fashion, where you have one carbon attaching. And so these formally are negatively charged ligands, right? Because I mean, look at this benzene. Benzene, for example, we know is C6H6. But when it's bonded in this way, it's C6H5 minus, right? We removed one of the hydrogens to get to this point. And so these are bonding via just sigma donation. It's a pretty straightforward type of bonding, sigma donation from the ligand to the metal via sort of that lone pair or that negative charge, right? That's formed. Um, these sort of 801 hydrocarbon ligands are prone to undergoing what's called beta-hydride elimination. So that looks like this, where if you have a hydrogen in this position on your ligand, it can rearrange to make a metal hydride, and then these two electrons can collapse into an alkene that can bond side on. And we'll talk about that on the next slide. But for this reason, because these eta-1 hydrocarbon ligands are prone to beta-hydride elimination, if you have ligands that don't have hydrogens, they're going to be more stable. So an example would be right here, right? There is no hydrogen that can collapse and do this sort of reaction when you have a benzene ring um, attached there, right? Because that's going to get you some, unstable benzyne type structure, right? If you're going to try to do this right here, this part, right? That's not going to be stable. So we're talking about, normally just sort of alkanes and things like that. Alkenes and alkynes can also undergo eta-2 side-on bonding, and so that's what you saw as a product of the beta hydride elimination. And in this bonding, you can have pi donation from the alkene. So that's talking about those two electrons in the double bond, in that pi bond, donating into the metal. But there's going to be an anti-bonding orbital associated with that pi bond, with that double bond, that can also accept, it has the right symmetry to accept electron density from the metal. And so you can have both of these cases. And just like for the hydrogen ligand we saw in the last video, where if you had significant pi back bonding, that could actually break the hydrogen ligand and give you, extreme case where you had two hydrides. The same thing is true here. You can break that double bond and instead make two bonds and make this metallocene, which is, sort of a cyclopropane type of analog. And so there's a continuum of bonding from this structure to this structure. Maybe you can represent it at like this, right? Depending upon how much pi back bonding you have. Here having a lot of pi back bonding, here not having any pi back bonding. The alkyne ligand, the eta-2 alkyne ligand is particularly interesting because you can have variants of that are 2 electron donors. One of the pi bonds can do pi donation, or you can have variations on that are 4 electron donators, where both the double bonds, the double and the triple bond, are donating, via this pi fashion. So that's pretty interesting. Oftentimes, you can do the you can use the 18 electron rule to try to predict, which type of bonding 4 electron donator for an alkyne or 2 electron donator for alkyne might be more stable. You can also have, multiple double bonds in the same ligand, okay? And here we're just considering non-conjugated systems. Later on, we'll talk about conjugated systems. Of course, these are non-conjugated because they're too far spread out, right, for you to do arrow pushing and delocalize the electron density there. But so here are some common examples. Cod is really common. So like nickel cod is a common precursor to making a lot of other organometallic complexes. The cod ligand is nice because it binds strong enough to make, in a lot of cases, like air stable complexes that aren't super reactive. But it's a weak enough binder that you can still do chemistry with it, right? It's not just like a rock that doesn't react at all. So cod is a useful precursor. So a lot of times you'll make nickel cod first, if you want to do like nickel chemistry, for example, and then do some other reactions after that. So in the next video, what we'll do is we'll start going into the bonding of different conjugated alkenes. Here, you're basically just treating cod as a 4-electron donor that's basically operating like two separate alkenes. Now they are tied together in space by these carbon atoms, but that's okay. That just confines the structure a little bit, can confine the geometry and the coordination number a little bit. But fundamentally, it's just behaving like two neutral side-on, eta-2 alkenes.